SNS College of Technology, Coimbatore. Today we are going to discuss about image restoration, image denoising. Okay, first of all, we are going to discuss about restoration in the presence of noise only. It is known as denoising. In this, we are having mean filters, arithmetic mean filters, geometric mean filters, harmonic mean filter, and counter-harmonic mean filters. In this arithmetic mean filter, g of x comma y is the corrupted image and sxy is the mask. Geometric mean filters, it tends to preserve more details, and harmonic mean filter, it works well for salt noise but fails for pepper noise. Contra-harmonic mean filter, Q represents the order of the filter. Positive Q works for the pepper noise, negative Q works for the salt noise. Q equal to 0 arithmetic mean filter, Q equal to -1 harmonic mean filter. And here in this diagram, it represents corrupted Gaussian noise, mean filtering, and geometric mean filtering. And in denoising, corrupted by pepper noise, corrupted by salt noise, and 3 cross 3 contra-harmonic if Q equal to 1.5 and if Q equal to -1.5 are represented here. Okay, here the results, it indicates selecting a wrong sign in contra-harmonic filtering. First one represents the filter size of 3 cross 3, Q equal to -1.5, second one for Q equal to 1.5. Okay, in filters based on order statistics, we have median filter, max and min filter, midpoint filter. Median filter, it represents 50th percentile of a ranked set of numbers. Max filter uses 100th percentile of ranked set of numbers. It good for pepper noise removal, and min filter uses the 1 percentile of a ranked set of numbers. It is good for removing salt noise. And midpoint filter, it works best for noise with symmetric PDF like Gaussian or uniform noise. Okay, here this image, it represents the corrupted by salt and pepper noise image, and 1 pass median filtering, 2 pass median filtering, and 3 pass median filtering. Okay, and also here this example, it denotes the corrupted by pepper noise, corrupted by salt noise, max filtering, and min filtering. Here we have different filtering images as outputs. Okay, and alpha trimmed mean filter, we have it is very useful in situations involving multiple types of noises like combination of salt and pepper and Gaussian. Okay, in denoising, we have corrupted by additive uniform noise as an example, and added salt and pepper noise in example, and 5 cross 5 mean filtering, 5 cross 5 median filtering, 5 cross 5 geo mean filtering, and 5 cross 5 alpha trimmed mean filtering. Also, we have an example. And adaptive local noise reduction filtering, here in this filtering operation, it changes at different regions of an image according to local variance calculated within an M cross N region. Okay, here we have an example for geo mean filtering, adaptive filtering, corrupted by Gaussian noise, and mean filtering. Okay, adaptive median filtering, here it is effective for removing salt and pepper noise. Both salt and pepper noise we can remove with the help of adaptive median filtering. The density of impulse noise cannot be too large. Here in adaptive median filtering, here the notations is at minimum gray value in SXY, and Z max represents maximum gray value in SXY. Z mid median of gray levels in SXY, ZXY gray value of the image at XY, S max maximum allowed size of XY. Okay, first one, in adaptive median filtering, we have 2 levels of operations, level A and level B. Level A, it is used to test whether Z mid is a part of SNP noise, FS window size is increased. Used to second one, level B, it is used to test whether ZXY is part of SNP noise. If yes, apply regular median filtering. Okay, here we have an example for image corrupted by salt and pepper noise with probabilities of PBV equal to 0.25. Result of filtering with a 7 cross 7 median filtering, and result of adaptive median filtering with S max equal to 7. Okay, here in this section we have studied about low pass high pass filters for image enhancement, and band reject, band pause, and notch filters as tools for periodic noises reduction or removal are to be studied. in this section. And band reject filters, it can remove or attenuate a band of frequencies about the origin of the Fourier transform. Similar to those LPFs and HPFs, we can construct ideal, Butterworth and Gaussian band reject filters also. Okay, here we have band reject filter. H of u comma v, it is equal to 1 minus e power minus 1 by 2 multiplied with d squared u of u comma v minus d naught squared divided by d of u comma v multiplied with w. Here we have an example for band reject filter. Image corrupted by sinusoidal noise, a spectrum of the noise, and band reject filters. White represents the 1, black represents 0, and the result of filtering. Okay, and we have notch filters that pass rather than suppress, and here NR filters become high pass filters, and also it can be used for low pass filters too. Okay, here we have an example for notch filters. You can see the effect of scan lines, spectrum of image, and inverse Fourier transform of NP filtered image, and we have notch pass filter and result of NR filter. Okay, here we have an example for optimum notch filtering, and in ideal case f of xy, it is equal to g of xy minus e2 of x comma y. In optimum notch filtering, here f cap of xy, it is equal to g of xy minus w of xy eta cap multiplied with x comma y. Okay, it represents a modulation function introducing for optimum notch filtering. Okay, optimum notch filtering, here points on or near edge of image can be treated by considering partial neighborhoods. Okay, to apply optimum notch filtering, we can get like this. Here we have an input image g of x comma y, and we have noise eta cap of x comma y. Here we have filtered output like this. And we have Fourier spectrum without shifting of an image for an example of optimum notch filtering. And we have Fourier spectrum of n of u comma v and the corresponding noise interference pattern eta of x comma y. Here we have image size 512 cross 512. Here a equal to b equal to 15 with the noise. Here the second image, it shows the optimum notch filtered output. And also we have linear position invariant degradation. Here we consider the degradation model g of x comma y, it is equal to h of f of x comma y plus eta of x comma y. Here many type of degradation can be approximated by linear position invariant process. Here extensive tools of linear system theory are available. So here in this situation, a restoration is image deconvolution. Okay, next we are going to discuss about estimating the degradation function. Here we have three types. One is observation, second one is experimentation, and third one is mathematical modeling. Okay, here we have an examples for estimating by experimentation and also estimating by modeling. Here we have negligible turbulence and mid turbulence and high turbulence, and we have low turbulence values for the function of h of u comma v, it is equal to e power minus k multiplied with u square plus v square whole power 5 by 6. Okay, by using inverse filtering, the simplest approach for restoration is direct inverse filtering. From this we can know the degradation function. We cannot recover undegraded image. If the degradation has 0 or very small values, then the ratio n by h could easily dominate our estimation of f. Here the function is f of u comma v is equal to g of u comma v by h of u comma v. Here one approach to get around 0 or small value problem is to limit the filter frequencies to value near to the origin. Here we have inverse filtering, degraded image, full inverse filtering, and filtering with h cutoff outside of radius 40, radius 70, and for radius 85. Based on the applications, we can use either 70, 40, or 85. And minimum mean square error filtering, it is called linear filtering. Here this approach, it incorporates both the degradation function and statistical characteristics of noise into the restoration process. Here we use E square, it is equal to E multiplied with F minus F cap the whole square. The objective is to find an estimation for F such that minimized E power 2. Here the image and noise are considered to be a random process. Here we have an example for linear filtering, full inverse filtering, radially limited inverse filtering, and we have finally the fully linear filtering. K was chosen interactively based on because it is a random process, so here K was chosen interactively. And here linear filtering, we have reduced noise variance when compared to the inverse filtering. And next one is geometry transformations. Here we have two things. One is spatial transformation, another one is gradable interpolation. We have discussed about spatial transformations and gradable interpolations in the previous classes. We just go through this, and this shows the geometric transformations of the input image. That's it. Thank you.